Okay, welcome back. We are in the middle of renormalizing the electroweak standard model, and in particular we are in the middle of setting up the so-called on-shell renormalization scheme. In principle, the basic idea is exactly the same as in QED, where we discussed everything, and we can follow the role model of QED in basically all steps. But there are way more interesting details which are subtle and which we need to discuss in order to be really able to apply the on-shell renormalization of the standard model in a secure way, also maybe at higher orders than one loop. Here I already wrote down the next section title, which is the on-shell renormalization conditions, where we write down what the actual conditions are which need to be fulfilled later on. And here are already some notes that are of interest to keep in mind whenever you set up a renormalization scheme for any model, which might not be the standard model but some extension thereof. And so in principle you always need to be aware of redundancies in your renormalization conditions, and in the best of all cases you should avoid such redundancies. And let me just give you an example of such a redundancy. So if we have alluded to this, if you have, for example, a matrix valued field renormalization with a matrix valued square root of z, and you multiply that with a matrix valued unitary matrix, then you would say, okay, I renormalize the unitary matrix, and on top of this I renormalize a completely general z factor matrix. Then if that is all you do, that is redundant, because multiplying a general matrix by a unitary matrix of course gives just another general matrix, and therefore there is no way, if that is all you do, to determine the two matrices independently. So if you do something like this, you at least need to be aware of it or avoid it. We have done that for the electroweak standard model. Then you need to choose renormalization conditions, and they should satisfy the property that they of course fix all the renormalization constants that you have introduced, but they should fix them in a consistent way such that you do not get equations like requirements which contradict each other, such that you cannot fulfill all requirements that you have imposed. That in essence means that you should impose exactly the same number of renormalization conditions as you have renormalization constants at your disposal. And that is obviously non-trivial in the case of complex models like the standard model or extensions. And the proof that we will give that we have done it correctly is simply by evaluating all the renormalization constants. We will see that there are solutions for all of them. The solutions are unique, and then all the on-shell requirements are fulfilled. Then a final remark, we saw that already in QED, not all conditions that you might like to impose can be imposed in the QED. It was the masslessness of the photon for which we could not impose an on-shell condition, but the masslessness of the photon holds anyway because of a Watt identity. And something similar will also happen in the standard model. So let us now discuss the on-shell renormalization conditions. And the statements are basically obvious if you know the ones for QED. So let us begin with masses and fields in the bosonic sector. Bosonic are the vector bosons and the Higgs fields. And so let us first say we require in this more explicit form that we once alluded to also in QED, where we have a polarization vector epsilon nu of q times the photon or vector boson two-point function VV prime for either two equal or two different vector bosons at momentum q, and if we apply that at q square equal m vector boson square, that should be 0. Okay. So, and this epsilon is a polarization vector which is transverse, and so this condition basically is only a condition for the transverse part of the vector boson self-energy, whereas the longitudinal part is completely projected away. There is no condition for the longitudinal part. Then similarly, for the Higgs two-point function at p square equal capital mh square equals 0, that is the on-shell condition for the Higgs boson mass. Then we have conditions on the derivatives, and so I formulate them as basically conditions of on this external line in Feynman diagrams for S matrix elements, and so this is 1 over q square minus mv square times a diagonal self-energy Vv mu nu at q times again a polarization vector epsilon nu of q at q square equal mv square. That should also vanish. So again, this is only a condition for the transverse part of the vector boson self-energy, and here please note that we only have diagonal self-energies appearing, Vv with the same V, whereas here we also have off-diagonal self-energies appearing with Vv prime. This is one of the subtleties which are not immediately obvious, and you might count in the end that it would not be possible to impose also yet another condition on Vv prime here. That would give too many conditions which cannot be fulfilled. And on the other hand, if you impose that only for the diagonal ones, you do not have enough conditions. So such comments apply, and these are things that you need to figure out by going through the detailed analysis, and we will of course prove that this is exactly the right thing to do. Finally, for the Higgs self-energy, we require this condition. Which essentially also means that the derivative of the Higgs self-energy at on-shell value vanishes. So these are direct generalizations of the corresponding conditions for QED. There are conditions which fix the location of the zero of the two-point function, which is equivalent to fixing the pole of the propagator and therefore the physical mass, and some other conditions on the residue of the propagator. Then next there is the condition on the Higgs tadpole. Which is simply gamma h, the one-point function, equals 0. And there is at the moment, since a few years, quite some discussion in the literature about possible ways to renormalize tadpoles. So let me just say what happens otherwise if you do not impose this. So if you do not impose that the tadpole vanishes, then the interpretation of those one-particle irreducible green functions changes. Only in this case are the two-point functions the inverse of the propagator. If that condition is not met, those are not the inverses of the propagators, and therefore these conditions do not correspond to actually physical masses. And so in these equations one should modify this. For example, the Higgs self-energy or this gamma HH should become not just the sum of one-particle irreducible green functions, but this plus such a contribution, where you emit a tadpole from a propagator. And this is not a one-particle irreducible diagram, but it contributes to the two-point function, and it contributes to the propagator green function, and therefore it contributes to the location of the pole of the propagator and to the mass. So, and by setting this renormalization condition, we eliminate such tadpole Feynman diagrams, and then it's correct to express the mass conditions by the 2.1 pi green functions. Okay, then the same for the fermions. So for the fermions, we also require the analog to QED, gamma FF, at P slash equal MF should be 0, and the following 1 divided by P slash minus MF gamma FF of P times a spinor U of P at P square equal MF square, that should vanish. And so the first condition again means, like in QED, that the 2-point function has determinant 0 at MF, so the MF corresponds to the pole of the propagator and therefore the physical fermion mass, and that sets the residue of the external propagator to 1, such that we do not get corrections in the LSE reduction formulas. And here in QED, I told you that there is a simpler way to write this condition. Here we write the explicit form because the self-energy has a more complicated structure because of the left and right-handed projectors, or gamma 5, which appears in it, and therefore one should calculate with this more explicit form. The final renormalization condition, as in QED, is about charge renormalization. And here we impose the identical renormalization condition as in QED. So we impose the following on-shell condition, namely you take an on-shell spinor U bar times the 3-point function gamma mu AFF evaluated at the momenta 0, P, P. And then again we multiply with an on-shell spinor U of P, and that is applied at P square equal the fermion mass square. And that whole thing should be equal to tree level, equal to U bar of P. Now I need to check something. Maybe let me. Yeah, minus EQF gamma mu U of P. And of course, if we would apply this for all fermions, so okay, first of all, the interpretation is as in QED, we require that on-shell all loop corrections to the 3-point function with a photon vanish. But there are many fermions, and before we have established charge universality, we cannot impose many conditions on charge renormalization. We can only impose one condition, and therefore we impose this condition for the electron specifically, F equal electron, and later we will ask ourselves whether some relationship like charge universality holds, because in QED that was an important output of the Slavnov-Taylor identity, and maybe the same is true here as well. So this is the complete list of renormalization conditions for the standard model with one generation of fermions where there is no CP violation and no CKM matrix. Okay. And now let me give you a few more comments. So a few comments to the formulation of the conditions which are specific to the standard model and which do not apply to QED. So one key property of the standard model is that there are unstable particles. So most of the particles actually are unstable, in particular out of the particles here, W plus minus, Z Higgs, but also most fermions, top quark, bottom quark, and so on. They are all unstable. And okay, if we have one generation, some fermions are stable, but anyway, so there are many unstable particles in the standard model. And that means that those one particle states that we normally consider, they do not really exist. So these particles do not actually correspond to energy eigenstates and to eigenstates of the p-square operator. So these are not really eigenstates of this operator. So this is the operator p mu, the Casimir operator of the Poincaré group. Eigenstates. But rather they are resonances, strictly speaking. And therefore, the poles of the full propagators, they are not really at the mass in the way you might expect. So they are in the complex plane. First of all, not on the real axis, in the p-square plane, but the poles of the propagators are at complex values of p-square. And in order to see the pole, actually, you have to go to an unphysical Riemann sheet, so you do have to do analytical continuation of your green functions in the complex plane in a certain way. So this is called unphysical Riemann sheet. And that was discussed actually in our quantum field theory lecture 2019. So I refer to this quantum field theory 1A from 2019 and 20. And there we discussed this in lecture 13 or section 422, where we discussed exactly this situation. What it means is that the inverse propagators such as gamma HH for the Higgs boson have an imaginary part. And technically, this imaginary part is related to this plus I epsilon prescription in the propagators of Feynman diagrams. So for example, this imaginary part would change sign if one would change sign in the plus I epsilon prescription of the propagators. So therefore, one has to say that our conditions that I wrote down, they are not strictly speaking possible to impose. We need to modify them a little bit. And I will, however, leave this notation as it stands and tell you various ways how to make it fully consistent at all orders. Strictly, there are two options. So the first option is we drop the imaginary part of this two-point function gamma HH, and we should only drop the imaginary part from this plus I epsilon prescription, not from complex CKM matrix elements if we would have 3 generations. We do not have complex CKM here, but in general there might be complex parameters in the CKM matrix, and then we should only drop the imaginary part coming from these plus I epsilon prescriptions, the so-called absorptive parts, and that is what is often called real part tilde of such 2-point functions. So we consider the real part tilde of these 2-point functions, and then in those on-shell conditions we would replace everywhere the 2-point functions by their real tilde parts, for which we can then impose the on-shell conditions. So then we would consider the 0 of real part tilde gamma HH of p square for real p square. So then it is clear that since the real part of gamma HH of p square, so you have a real function of a real variable which is somehow continuous, therefore for some real value of p square this real part will have a 0, and that is the 0 which we are searching for in the on-shell renormalization condition. So that is one possibility, and that is what we will assume here. For simplicity and at the one loop level, this is fine and causes no complications. So the other option is to go into the complex plane and take this more seriously even. So then we would require that the determinant of, or let's say in the Higgs self-energy, we would simply say gamma HH of p square equals 0, and here I mean really the full complex quantity that is now complex. So we look at, and so then the complex part is real and imaginary part of gamma should be 0 simultaneously, and then of course it is non-trivial to find a solution to that equation, and in general the solution will be in the complex plane, so you need to go to complex values of p square in order to solve that equation. And so then you get a solution for p square which is then called, let's say, curly mh square, and this curly mh square is complex, and we can decompose it into real and imaginary parts. We can write ordinary mh square minus I mh times gamma h, and then the interpretation is immediately that the real part of this curly m square corresponds to basically a resonance peak if you have a Breit-Wigner resonance in a scattering process, and this here corresponds to the width of the Breit-Wigner peak. So this is then exactly the interpretation and also the outcome of the behavior of the propagator. So the full propagator will behave like 1 over p square minus this, and then you know from other lectures and other physics discussions the interpretation of those two things. So this would be a complex mass square that is what you would then typically call the actual mass of the particle, which is a real number, and it corresponds to the location of the resonance peak, and that here is the width of the resonance peak, and at the same time it is the width of the particle, in other words 1 over the lifetime of the particle. So, and this is discussed in the literature that I gave you, but let me also give you another reference where it is also discussed in some detail in a maybe complementary way. So see also if that is a paper from us, colleague Kraus. So where we discussed the case of the minimal supersymmetric standard model and its all-order renormalization in such an on-shell scheme, where we also spent some time to discuss these issues. So this is one remark, and the second remark is on the unphysical sector. So we will not spend too much time, actually almost no time at all on renormalizing the unphysical sector. So let me simply say more details. See literature, including also this just mentioned reference, where we also discussed the renormalization of the unphysical sector in great detail. And I remark just the following. We can again require that the gauge fixing Lagrangian does not renormalize. And that fixes the renormalization of these gauge fixing parameters delta zeta and delta xi that appear in the gauge fixing Lagrangian. So they must behave in such a way that overall in combination the gauge fixing Lagrangian doesn't renormalize. And then we can impose conditions such as the following, namely basically the analog of the gauge boson renormalization just for the Faddeev-Popov ghosts. So for every gauge boson there is a corresponding ghost and anti-ghost, and we can require this. So all the diagonal and off-diagonal ghost self-energies at the corresponding masses are 0. Diagonal and off-diagonal, and also the derivatives of the diagonal ones. They are 1. By the way, did I make a mistake here? I think sorry about this, I made a mistake here. So of course, here in those derivative conditions, since these gamma symbols here contain tree level, that should give not 0, but it should give the same as a tree level, which is in this case minus epsilon mu, and in the Higgs case it is 1, and in the fermion case it is u of p. So sorry about this. So the difference is whether you count tree level as well inside of gamma, then at all orders the result must be equal to tree level, otherwise the loop corrections must vanish. Okay, and therefore here as well the right hand side should be 1. So but here there is also a difference, namely we cannot pre-impose what the value of the ghost masses are. They are an output of the calculation coming from the choice of the gauge fixing. So that is another subtlety and difference to the left hand side. So this MCV is cannot be chosen freely. It follows from the gauge fixing. So what that means is that once we have fixed the gauge fixing by saying, for example, the gauge fixing does not renormalize, then the actual masses of the ghosts are fixed. They cannot be changed anymore by us. We cannot impose what the masses are after imposing the gauge fixing Lagrangian. And that means that the p-square values at which the determinant of the ghost two-point matrix vanishes, they are fixed. So then in principle we should determine what are the actual values of the ghost masses, and once we know what the values of the masses are, we go to this condition and say, at this value of the mass, I require that the off-diagonal and diagonal self-energy simultaneously vanish. This is then an additional condition, because the mass value only means that the determinant of the matrix vanishes. It doesn't mean that each matrix element itself vanishes. And that is the meaning of this condition here. That is different here in the vector boson case. Here we start by saying I require that the value of the Z mass is 91 GeV, and then at this value mz equal 91 GeV I impose this condition, and so on. Here we cannot do that. Okay, so this is the next step. Any questions so far? Does the technology still work? Okay. So then let us go to the next section. I told you that it is not trivial that all renormalization conditions can be fulfilled and that they determine all renormalization constants unambiguously, but that is the case, and we prove it by explicitly evaluating the results for the renormalization constants. And let us do that first for the bosonic sector, which is exactly this sector that you see here, including the vector bosons and the Higgs. And afterwards, let's focus on the other parts of the theory. So the more complicated part of this is obviously the gauge bosons. So let us start with the gauge bosons. And in order to deal with them, we do a covariant decomposition. We also did that in QED, but let me write it down. So here we do it differently than in QED. So let me write it for the self-energies with or without hat. Let's write it without hat. It applies to both cases. Sigma VV prime mu nu of Q. So this symbol stands for the one particle irreducible self-energy without tree level between two vector bosons V and V prime, and with two open Lorentz indices mu nu and a momentum Q. So this has a transverse part and a longitudinal part, and we write it differently from QED in the following way. G mu nu minus Q mu Q nu divided by Q square times sigma T for transverse VV prime of Q square minus I Q mu Q nu divided by Q square times sigma L VV prime of Q square. Okay. So the difference to QED is twofold. First of all, in QED there was no longitudinal part. We proved by a Slavnov-Taylor identity that the self-energy is transverse, and therefore such a term did not appear in QED. There was only the transverse part, and the transverse part we wrote it like Q squared G mu nu minus Q mu Q nu without the denominator. And that built in immediately the regularity at Q square equals 0. So here it is different. There exists a longitudinal part. We know it from tree level already because the Z and the W, they have such a longitudinal part, and that is retained also at higher orders. And therefore, there will be terms which just go like G mu nu without any Q square prefect rule. They correspond to mass terms in the self-energies. And so therefore we need also this denominator, and that is singular, and therefore the regularity at Q square equals 0 has now an important implication, namely at 0 the transverse and the longitudinal self-energies are equal at q square equals 0. That is something that can be used in explicit calculations. Okay, but that is our ansatz, and then we can decompose our renormalization conditions into conditions for the transverse part and the longitudinal part. And let us do that now. Let us rewrite our renormalization conditions for sigma hat VV prime. So we see them here. The first condition multiplies, so sigma is the one loop or higher contribution to gamma. Gamma is simply 3 level minus sigma. Okay, then therefore this means epsilon times sigma must be 0, and the epsilon is transverse, therefore the epsilon annihilates the longitudinal part. It drops out of the renormalization condition. The entire renormalization condition only applies to the transverse part, and it reads then sigma hat transverse VV prime at, okay, let me write it down explicitly, so WW at p square equal mw square equal 0, and the condition for the derivative, again only the transverse part enters, and then the prefactor simply means taking the derivative, so d by dq square of sigma hat transverse WW at p square equal mw square. That should also be 0. So these are the two conditions for the W boson. Similarly, we can look at this diagonal term here, VV prime for the Z boson. So let's put here VV prime equal to ZZ. Then we get a diagonal condition for the Z, which looks identical. Sigma hat ZZ at mz square equals 0, and derivative d by dq square of sigma hat zz transverse at mz square equals 0 as well. Then
طبعا هنا هذه المساواة بين السيجما ترانسفيرس والسيجما لونجيتودينال، أنا ذكرت أنه يمكن عدم مساواتها في كتابي وفي نظريتي بسبب أن السيجما لونجيتودينال يعني يمكن أن يكون combinations of many unphysical state and physical state. طيب هنا ماذا يحدث إذا كانت السيجما ترانسفيرس لا تساوي سيجما لونجيتودينال؟ فتصل أنا بعد سأفرق هذه السيجما على زيادة في الطاقة، وسنصل في النهاية إلى نفس النتيجة، لكن ما أريد أن أقوله أن هذا ينعكس على شيء ما، ينعكس على كتلة البوزون، فإن الكتلة تكون أقل والطاقة تكون أعلى. هذا البوزون مطرود من التفاعل، مثلا الدبليو مطرود من التفاعل، الكتلة تكون أقل وطاقة تكون أعلى، وبالتالي في نهاية التفاعل اللي هو عند بي سكوير يساوي ام سكوير سنصل إلى الكتلة الحقيقية للبوزون، لكن هنا يحصل التحلل فورا. ربما التحلل يحصل قبل ذلك لأنه لدينا طاقة عالية، وعندما يحصل حدوث التفاعل اللي هو أونشيل يكون قد تحلل هو على هذا البوزون قبل أن يصل هذه الحدود. طيب فيما ينعكس ذلك؟ ينعكس ذلك في أنه يعطينا جسيمات مختلفة الطاقة أو مختلفة الكتلة، طيب أين نجد هذا في هذه المعادلات؟ مفترض أننا تظهر لنا هذا الأمر في هذه المعادلات مباشرة، أننا يظهر لنا الكتل المختلفة والمتباينة. طيب فعلينا أن نستنتجها من هذه المعادلات. طيب عند الترانسفيرس يساوي 0 اللي هو عند الأونشيل ترانسفيرس يساوي 0، قد يكون السيجما L لا تساوي 0. حاصل الطرح بينهما نعبر عنه بفرق الكتل، يعني عندما تصل السيجما تي الزيرو ربما يكون السيجما ال وصلت إلى 0 قبلها، وبالتالي يظهر فرق في الكتل، وبالتالي يظهر هذا الفرق عبارة عن فرق في الطاقة اللي هو بي سكوير يساوي ام سكوير عن شيل. هنالك ربما يكون بي سكوير لا يساوي ام سكوير، يساوي أقل من الام سكوير. هنا يحصل التحلل. عندما يحصل التحلل فإن الطرح بين السيجما تي والسيجما ال تعطينا النتيجة، تعطينا فرق في الكتل، تعطينا هذه فرق في الكتل. يمكن العلماء يبحث عنها، فكتلة البوزون دبليو معروفة هي 80.3، لكن إذا كانت الطاقة عالية فإن البي قبل أن تصل أونشيل ربما تتحلل هي، وإذا وصلت البي قبل أن يعني تتساوى أو تطبق هذا الشرط أن بي سكوير يساوي ام سكوير، وقبل البي أن تصل إلى الام تم التحلل، فهذا ينتج عن أن الام ذات نفسها لم تصل إلى هذه المرحلة. يعني هذا شرط مطبق، إنما هو وصلت بي يساوي ام بي سكوير يساوي ام سكوير يحصل التحلل تعطي النواتج. ربما ام ذات نفسها لم تصل هذه المرحلة بالنسبة للدبليو، فبالتالي البي سكوير يساوي ام سكوير، لكن الام سكوير لا تساوي 80 فاصل. فهذا يبين في ماذا يظهر في الطاقة العالية. بالرغم أن بي فيها سرعة، يعني البي هي فيها سرعة، والبي أيضا تعبر عن معدلات تدفق المكان. فكلما زادت معدلات تدفق المكان كلما زادت البي. ومعدلات تدفق المكان ترتبط بماذا؟ ترتبط بعمق التفاعل. كلما زاد التفاعل عمقا زادت هذه المعدلات تدفق المكان، إذا البي ستكون كبيرة. فبالتالي يعني يمكن العلماء أن يتحققوا في هذا الأمر، فإن البي أثناء انتقالها من وسط التفاعل إلى نهاية التفاعل اللي هي عند البي يساوي ام بي سكوير يساوي ام سكوير، هنا تتحلل الدبليو مباشرة لتعطينا فرق الكتل هذه في بين السيجما تي والسيجما ال، تعطينا هذا الفرق في هذه الكميات إلى الفرق في الكتل بالنسبة للكواركات. لأن نحن نرى أن هناك فرق كبير جدا بالمناسبة بين السترينج مثلا وبين الأب والداون، فرق كبير جدا. يعني هذا السترينج لا، السترينج ليس فرق كبير، السترينج عبارة عن 106 ولا 104، وهؤلاء يعني 4.8 وذلك 3.5 ميجا كلها ميجا. لكن نجد أن البوتوم هناك فرق كبير بين البوتوم وبين السترينج. سترينج 100 والبوتوم 1.2 فرق كبير بين السترينج. وهذا ربما يدل على انه الفرق بين الاي تي اللي هو سيجما ترانسفيرس والسيجما لونجيتودينال يكون هذا الفرق كبير. هذا الفرق كبير يمكن للعلماء يبحثوا في هذا. فهذا تنافي السلافنوف ايدنتيتي والوارد ايدنتيتي ايضا، لكن في النهايه يتم التحلل بالنسبه لانه الانتقال من فضاء التفاعل الى الفضاء رباعي الابعاد بهذه الطاقه العاليه يجب ان يتم فيها التحلل. بالتالي ينتقل هذا الجسيم هذا البوزون ويصل الفضاء العادي، يعني الفضاء الفري بارتيكل يصله مبكرا أكثر من يعني إذا اعتبرنا السيجما ترانسفيرس. فهذا الفرق يعطينا هذه الكتل.
For the photon, let us look at the diagonal term sigma hat AA transverse times at p square equals 0 also has to vanish, and d by dq square sigma hat transverse AA at 0 needs to vanish as well. This is the same condition as in QED. But here let me write a note. See later, this is connected to a Ward or Slavnov-Taylor identity. So this condition, which looks like a photon mass condition, that actually cannot be fulfilled by choosing renormalization constants. It must be fulfilled automatically from a Slavnov-Taylor identity. So we will discuss that. Then let us look at the off-diagonal elements. We have now dealt with all diagonal elements, VV, WW, ZZ, AA, and here. And then there are off-diagonal conditions, namely off-diagonal VV prime, and the off-diagonal ones are photon Z mixing. So there are two conditions, namely either you have here the photon mass, which is 0, or the Z mass. And then you get two conditions, and one condition is the following: sigma hat transverse AZ mixing at 0 equals 0, and the other condition is sigma hat transverse AZ at mz square is also 0. So you see here that we impose two independent and different conditions on the AZ mixing self-energy, namely it should vanish at two different momenta. In other words, it should vanish at both on-shell mass values. So we have eliminated the mixing for both on-shell values of the momentum. So then this is a translation of our renormalization conditions to the self-energies, and for the self-energies we have already determined how the renormalization constants enter. Of course, that was on the blackboard the last time, so we should now go back to what we wrote down. Namely, we have written down the renormalization constant contribution to all these sigma hats. And then we should now write down sigma without hat plus the counter term contribution is 0, and that will fix somehow the renormalization constants. And let me just give you the results, since it's not on the blackboard, so there is no way reasonably to derive it. But let's write it down and then discuss it. So if we apply it here for the W mass, then we see something very simple. WW transverse without hat, so unrenormalized at p square equal mw square, and then all the renormalization constants drop out except delta mw square. So then we simply get a condition sigma transverse at mw square minus delta mw square is 0, and that is immediately solvable for the renormalization constant delta mw square in a simple way. And that is very similar to the case of the electron in QED. Then we also have derivative with respect to q square of sigma w without hat at q square equal mw square plus delta zw is also 0. And that is also basically the same form as in QED, and it immediately determines delta z in a very simple way. So, and you obtain this by just looking at the rules that we wrote down the last time. Let's go on for the z. Sigma transverse zz at mz square. Here actually the same thing happens, namely minus delta mz square equals 0. And here also exactly the same thing happens. With a slight difference that here the renormalization constant delta z, zz appears. So that is what you would expect, but it's kind of more non-trivial because we have this matrix valued z factor, and therefore we have these matrix elements delta z, zz, za, aa, and so on. And here indeed the diagonal field renormalization zz appears, as you would naively expect. But you can look at the formula, it explicitly comes out of the calculation. Now, what about the photon mass? In the case of the photon mass, we get sigma transverse AA at 0 minus 0 equals 0. And what I mean by this equation is that there is no renormalization constant available. So therefore that means that either the condition is satisfied automatically or we have a contradiction. And therefore we must prove later by a Slavnov-Taylor identity that indeed this condition is satisfied automatically, and the same was true in QED. So that is what I meant here, so see later. So we still need to see it even later than now. So then, but for the derivative, it's the obvious thing that always happens, sigma transverse AA at 0 plus the diagonal z factor delta zaa has to give 0, and then again this diagonal AA z factor is immediately determined in a simple way. Then for the mixing, AZ mixing, what happens here? AZ at 0. And so here, in order to understand this, you really should go back to the formula that we have explicitly derived. We've explicitly derived this counter term Feynman rule, which looks like this. Okay, so this sort of Feynman rule, we have written it down, and that enters here. And if you look at it, it depends on the momentum, and it depends on the mass counter term delta mz. And if you set the momentum to 0, then the counter term contribution is the following: minus mz square delta z za divided by 2. And that should be 0. Okay. And here is again this interpretation. The renormalization constant delta z za appears. And I told you already this has the interpretation that the renormalized photon field behaves in a way like the Z boson should behave. And therefore this constant multiplies a counter term proportional to the Z mass, even though we are looking at the self-energy involving the photon at 0 momentum. The other condition, sigma AZ at mz square, has the opposite effect. So if you set the momentum in this counter term Feynman rule to p square equal mz square, then this renormalization constant drops out and the other one comes into play, and it has the opposite sign, plus mz square times delta z az divided by 2 equals 0. And then you see that these two conditions in the last line, they determine uniquely both off-diagonal field renormalization constants. And you see that both conditions can be fulfilled. The renormalization constants are determined by different self-energies, namely AZ at either momentum 0 or at momentum mz square. So the result of this and that calculation will for sure be different, and therefore we get different values for this delta z ZA and delta z AZ. But if you look at it now with this set of equations, all the renormalization constants in this sector are unambiguously fixed. And that would apply not only at the one loop level but at all orders, because the structure of these equations does not really change, except that also products of renormalization constants appear. But anyway, the renormalization constants can be determined in the same way. But regarding this comment at the beginning, can we are the equations consistent? That means this condition here for the photon mass, can this be fulfilled? We cannot make sure by hand that it is fulfilled because there is no counter term at our disposal, so it must be fulfilled automatically. This is something to be done later. Let us end the section by looking at the Higgs sector. Which is way simpler, of course. So for the Higgs sector, we simply get, let me write it down immediately in terms of the self-energy, sigma without hat for the Higgs at the value m Higgs square minus delta m Higgs square equals 0. So that fixes, of course, the Higgs mass counter term. Similarly, d by d p square of sigma Higgs at p square equal m Higgs square plus delta z Higgs equals 0. That fixes, of course, the field renormalization constant for the Higgs. And then we have the tadpole condition, I times t plus I times delta t must be 0. That is the condition here, where this I times t stands for the one particle irreducible without counter term diagrams for the one point function with one external Higgs, so the tadpole Feynman diagrams. And then again, all renormalization constants are fixed. Okay. Now, and the remaining comments that we could write down here. So, what about the photon mass? Is it automatically 0, or do we get a contradiction? And second, what about, for example, Goldstone boson masses? As you see, we have not imposed a renormalization condition for the Goldstone bosons. They are actually, okay, sorry about this, but let me add one thing. Okay, no, let me not add it. But what about the Goldstone boson masses? They cannot be imposed because their values again follows from the gauge fixing choice, like the masses of the Faraday-Popov ghosts. What we know is that the masses of ghosts and Goldstone bosons are exactly equal at all orders. That is what we have proved in the other lecture. But what the value is, we don't know. And so then we cannot put this in as a renormalization condition. It comes out as an output. And at the value of the mass which comes out, we might impose a condition on the field renormalization of the Goldstones, but we will not discuss this here. So we will ignore that here because in general, if we are interested in one loop physical calculations, then the unphysical particles can only appear in loops, and therefore the unphysical sector does not have to be renormalized for a consistent physical one-loop calculation. Good. Let me clean the blackboard. Yep. Yes. So there are no infrared divergences at all in any of those renormalization conditions, neither in the ones for the mass. Let me take that back. At least there are no infrared divergences here in this 3-point function where you might expect some infrared divergences because the vertex between photon and fermions in principle at on-shell values contains infrared divergences, but since we put all three momenta simultaneously on-shell and the photon momentum is 0, the infrared divergences drop out, and this is actually infrared finite. So another thing about infrared divergences is that, for example, conditions like this, photon mass equals 0, mixing 0 at p square equals 0, those are infrared safe to impose, and the green functions which need to be calculated at p square equals 0, they do not involve infrared divergences, but on the contrary, it is actually very efficient to impose those conditions if you then want to prove the infrared consistency of your green functions at higher orders. So you can then, for example, prove by infrared power counting similar to ultraviolet power counting that the green functions are in general well defined. Now there is one problem which is completely common to the standard model and to QED, namely that charged particles like basically most of them, fermions in particular, but also the W boson, which couple to the massless photon, they have infrared divergences in their self-energies if you evaluate the derivative. So that means that ultimately the field renormalization constants for charged particles like the W, but also more importantly the fermion like electron, delta Z for the electron, that contains an infrared divergence in the on-shell renormalization scheme. And that is a fact of life. And it is part of this discussion of how infrared divergences need to be treated between real and virtual corrections. There, these field renormalization constants appear as a part of the loop corrections. And then, of course, 3-point functions like this appear, evaluated at momenta of the photon which are not 0, and then they also contain infrared divergences. This is part of the infrared divergence. The delta Z is part of the infrared divergence, and the sum of them is cancelled by adding real corrections in the computation of physical processes. So that is the general necessity for calculating physical observables involving charged particles, and that structure of this problem is the same in the electroweak standard model and in QED. But imposing the conditions by themselves is infrared safe. Yes, this is the practical procedure, such that the delta Z contains not only UV divergences but also infrared divergences. And then you keep track of those infrared divergences coming from the derivative of the self-energy in this way. Yeah, then if you would, I mean, this is not really, let's say, more tricky than in other cases, but what you normally would call the finite part is dropped. This finite part now contains an infrared divergence, And so if you just look in dimensional regularization at the 1 over epsilon poles, in case you treat infrared also using dimensional regularization, then MS bar and on-shell differ by 1 over epsilon poles in the renormalization constants. Because here this delta ZW would contain 1 over epsilon UV and 1 over epsilon IR, and the MS bar counterpart only contains 1 over epsilon UV. So that is a little bit tricky to compare. But since the structure of infrared divergences for QED and also here is much simpler than in QCD, it is often not really necessary or most efficient to treat this with dimensional regularization, but often one treats it using a small photon mass as a regulator. And then it's more transparent how to switch between MS bar and shell. But both is possible. Okay, let's go on with the fermion sector. And here I need to abbreviate a little bit. The evaluation of those conditions here for the fermions are really a little bit more tricky than in QED, and however I want to skip the details of that calculation. As I said, the basic problem is that the fermion self-energies contain gamma 5 and left and right-handed projectors, and then the evaluation is a little bit messy. So let me write down a covariant decomposition. So I times sigma f with or without hat will be decomposed into all possible covariants, and clearly the result can contain p slash, but it can also contain projectors, and so let me write p slash times left-handed projector times a form factor which I call sigma L f, which can then only depend on p square. Plus the same with a right-handed projector, sigma right f of p square. So this is the p slash part, which is decomposed further into left and right-handed. And the same for the non-p slash part. So the non-p slash part is written as I times p left times sigma SL f of p square, where SL stands for scalar and left-handed, and plus I times p right times sigma SR f of p square. Okay. And then you have 4 form factors instead of 2. You could equally well decompose it into gamma 5 and non-gamma 5 terms, which is of course equivalent. But this is the decomposition which actually comes out of the calculation and which we need to cope with. And in terms of that, the interpretation of those conditions is less obvious compared to QED. And so actually it's not even possible to evaluate the conditions without using something from fundamental quantum field theory. And let me just quote that without proof. Namely, CPT invariance relates the self-energies further. Namely, from CPT invariance, where we, let's say, again ignore this re tilde, which is this dropping the imaginary parts coming from the plus I epsilon prescriptions. They behave differently, but everything which does not come from those imaginary parts behaves as follows. Namely, sigma LF is equal to sigma LF complex conjugated. The same with R. sigma fr is equal to sigma fr complex conjugated, and the sigma SL scalar left is equal to scalar right complex conjugated. So there are these relationships. So 2 out of them are real, and the other 2 are related by complex conjugation. Here we have, in addition, not only CPT invariance, but we also have CP invariance without the T, because we have one generation and no CKM matrix. And if we have also CP invariance, then there follows a stronger condition, namely sigma SL is not only equal to the complex conjugated of the right-handed, but they are exactly equal. So they are also real. And then if they are exactly equal, SL and SR, then it makes sense to simply speak of a scalar fermion self-energy, sigma S, which is both the left and right-handed part. And then you can drop here the P left, P right. The 2 simply add up to some sigma S, a scalar part without gamma 5. And that makes then possible to solve those equations on the left, and the solution can be expressed in terms of the counter terms and these self-energy building blocks here. So let me just stress this holds here because we have CP invariance, and it was already used in the renormalization transformation. So maybe it wasn't used explicitly, but you might have guessed that when we write mass counter term delta MF, then what we mean by this is a real mass counter term. And so that is what we always use. The mass counter term doesn't have an imaginary part. And the fact that a real mass counter term is sufficient is connected to this CP invariance which holds. And then if we write down now the solution, then we will see that we get a solution for the real mass counter term. So let me write down the results of this analysis without going through all the details. You can find the details in all the literature that I've mentioned, starting from Aoki and then all the other papers from Denner and others. Yeah. So for the mass, we get the following, namely P right times sigma hat FL at MF square times MF plus P left sigma hat FR at MF square times MF plus sigma S F at MF square equals 0. So that is the direct outcome of the mass condition, where we have here also a hat. And if we plug in the renormalization constants, then we see that this equation is actually 2 equations, because obviously the left-handed and the right-handed part of the equation are independent. So therefore it decomposes into one equation for the left-handed part and one equation for the right-handed part, but they are equivalent, and they mean sigma FL plus sigma FR divided by 2, so the average, times the mass plus the scalar part Fs minus the mass counter term delta MF equals 0 at P square equal MF square. And then we can solve for the mass counter term delta MF. And you see that the mass counter term comes out to be real because of those conditions that we mentioned before. So that is consistent with CP invariance. And so all the two conditions come down to just one. Okay, and then the second one, which comes from the gamma 5 part, is then sigma hat FL must be equal to sigma FR at P square equal M F square. And that is then non-trivial, because we have no renormalization condition at our disposal. At least, yeah, well, let's first go on, let's see later. Then the field renormalization imposes the following. Without proof, we obtain P left times sigma FL plus P right sigma F right plus P left. Let me exhibit the field renormalization, delta Z F left plus P right delta Z F right plus the derivative with respect to P square of the following expression, which is a fraction divided by 2 of sigma F left plus sigma F right times the mass plus sigma SL plus sigma SR. That whole sum should be 0. Okay. And then again you get two conditions. One condition on delta Z F left and another condition on delta Z F right from the left-handed and the right-handed part of this equation. And in this case, there is a one-to-one correspondence. The left-handed part determines the left-handed set. The right-handed part determines the right-handed set. So both have a unique solution. And so unique solution. And sigma FL is equal to sigma FR is then in the end satisfied automatically. So if you solve the delta Z from the second equation, then you plug it into this equation for the renormalized left and right-handed self-energy, and you see that they become equal. So in this way, we have also dealt with the fermion sector. So, any questions to this? And actually, of course, here there would be the infrared divergences in this effective derivative here of the fermion self-energy. This evaluated on-shell has an infrared singularity, and so the delta Z renormalization constants, they contain infrared singularities from the massless photon. Good. And so actually deriving all this in detail is more effort, and it relies on those relationships that I've written down here. And however, that is the result. So it gives you a practical determination recipe for delta MF and for the two left and right-handed field renormalization constants. And it will be even more complicated if you have three generations and mixing between the fermions of the three generations. Then one would impose, again, diagonal conditions on diagonal self-energies like upwarp to upwarp, but also off-diagonal conditions like upwarp to jumpwarp, upwarp to topwarp, and so on. And then one would have off-diagonal matrix-valued Z-vector matrices, and they would need to be determined by diagonal and off-diagonal conditions. But let's stay at this one generation example, and let us go on if you do not have any further questions. Then the final thing that we can discuss today, at least to some extent, is charge renormalization, which we also discussed at length in QED, where there is an important and interesting Slavnov-Taylor identity or Watt identity leading to charge universality and to a strong technical simplification of the evaluation of this condition, such that in the end the charge renormalization constant is only determined in terms of 2-point functions instead of 3-point functions. And the dependence on the fermion that we have chosen to formulate the condition drops out of the calculation. And in the end, we see that the result for charge renormalization would be the same regardless whether we choose here electron, muon, tau, or up quark, and so on. The same is true in the standard model, but again, the derivation of that is way more complicated than in QED. It's really surprising how much more complicated the derivation actually is, and the amount of literature on the charge renormalization is quite amazing. So probably we cannot discuss all of it today, but let's begin the discussion. Maybe here. So the preliminary evaluation before knowing about this Ward and Slavnov-Taylor identity is as follows. So we have here this minus I times lambda hat mu for the electron is this one particle irreducible starting from one loop contribution to the photon electron 3-point function. So gamma is the thing which also contains 3 level, and lambda is the object which starts at one loop. And then our charge renormalization condition means that if we plug in lambda at this point, then we get 0 on the right hand side, because the full object reduces to 3 level at all orders, and so the loop corrections vanish. Therefore, we get a condition 0 is equal to the following, namely lambda. So the following equation is meant between u bar of p and u of p. So let us not always write the spinors u bar and u, but the equation is meant to hold between these two spinors, and then we have lambda mu e, I drop the minus I, plus the renormalization constant contribution, plus e qe gamma mu, that is the photon 3-level vertex, and that is multiplied with renormalization constants delta e over e plus 1/2 delta z AA plus delta z EL P left plus delta z E right P right. Okay, so this corresponds to the counter term contribution from the photon electron counter term, where we take the 3-level vertex and add all the renormalization constants corresponding to parameter and field renormalization. That is so far very similar to QED, actually the same up to the fact that we have left and right-handed fermions which behave differently. But that is not all. The renormalization of the photon electron vertex contains also a part which comes from the Z vertex and which is proportional to this mixing delta ZZA over 2. So as I said, this mixing means that the renormalized photon field behaves like the Z boson, and so we get a contribution that looks like this: E over 2 sine times cosine of the weak mixing angle times gamma mu, and then times CL E PL plus CRE PR. This here is really the 3-level Z boson vertex, 2 electron with these left and right-handed coupling coefficients which we have defined some lectures ago, and that is multiplied with the off-diagonal field renormalization constant. that is really the equation that we get. So it's quite complicated, and it involves a lot of renormalization constants. However, all of those renormalization constants are already fixed by previous calculations except delta E. So clearly that will give us a solution for delta E, but it is first of all not trivial that the equation can be solved at all, because it again has left and right-handed parts, and both must be satisfied in the end. And second, we see here that delta E is determined in terms of a 3-point function, and our hope is that we can eliminate the 3-point function in favor of 2-point functions like we could in QED. So, but at first we can record that clearly it fixes delta E uniquely. So that is the preliminary result. Now, let me today drop the Watt identity which holds from the sky without derivation, and possibly we will manage in the semester to derive it, but maybe not, but I will drop it here and then we can discuss its impact. So there is a Slavnov-Taylor or Watt identity, which looks like follows: U bar of P times lambda F mu at momentum 0 P comma P, U of P, where the momentum P is of course on-shell specific to the fermion, so P square is equal to mF square, where mF is the physical mass of the respective fermion. And so this, for any fermion, has the following value. It is the same as the same spinor U bar of P times the following: E times QF, so the QED charge, times the following derivative of the fermion self-energy of P, but first derivative with respect to P mu. So this is a derivative really with respect to the 4-vector P mu, which is different compared to the derivative with respect to P square or P slash, but here we have P mu. So the result is a Lorentz index quantity comparable to lambda mu on the left-hand side. Then we have minus E times CFL minus CFR divided by 2 times sine times cosine times gamma mu P left times the following: sigma transverse AZ at momentum 0 divided by mz square, then times the spinor U of P. So what you see here is that in QED you had a relationship between the 3-point function and the fermion self-energy. So the counterpart in QED reads exactly like this: the left-hand side is just equal to this object here on the right. That's the QED relationship, and we derived it explicitly from the QED Watt identity. In the electroweak standard model, we have the additional contribution which contains the mixing self-energy between the photon and the Z. The mixing self-energy is evaluated here at 0, and it has this weird coefficient. The weird coefficient is left-handed, gamma mu times P left, and it is related to the Z boson vertex. So it's almost like the Z boson vertex. So this is the Z boson vertex. So it has this prefactor, and it has C left, C right with P left, P right. Here we have the same prefactor E over 2 SC, but we have C left minus C right and both times P left. So that is this strange Watt identity which holds, and there is a long literature on establishing this. We can go through the details of this the next time, but let me just say what happens. So if we plug that in, we obtain between U bar of P and U of P, we obtain the following relationship for lambda. lambda f mu on shell is equal to the following. So you see here, this is the derivative of the fermion self-energy with respect to p mu. And if you go through the details, then this leads to exactly the same combination as the one that appears here in the determination of the field renormalization constants. So therefore, this object here reproduces exactly the left and right-handed field renormalization constants. So we get here minus EQF times delta z f left, p left, plus delta z f right times p right. So this comes from here. And the on-shell condition, of course, such that this is determined in terms of the delta z factors. Then this we can copy. Divided by 2 SC times gamma mu p left. And then this is, of course, our off-diagonal field renormalization constant between the photon and the Z. So this is exactly this delta Z ZA. So this is delta Z ZA divided by 2. And therefore, we have now fully related our 3-point function without counter terms to renormalization constants which we already know. So that is the magic of this Watt identity. So this is related only to field renormalization constants, and then we can plug in this knowledge into our renormalization condition. And let's finish with this. The above becomes, so the renormalization condition, if we plug here the result for lambda e, then you see lambda e becomes, first of all, the QED prefactor. I think I missed here gamma mu. So it becomes exactly this. So you see lambda, if you plug it in, it cancels exactly those contributions from the field renormalization constants. So let me highlight this. This is cancelled by lambda, and this is cancelled by lambda. And then the second line is not cancelled, but it is modified. So here, this term contains only p left, so it modifies only this term. What happens if I add that over there to this? It means the CL is subtracted and we add CR. So here it just replaces CL by CR, and then we get CR times p left plus p right, so p left, p right drop out, and here we only get CR. So, and then we should note that what is the value of the CR? CRF is actually minus the electric charge QF times the sine square. And if we plug in this, then we get here the CR times the unit matrix, and CR is the electric charge. And then we obtain 0 is equal to E times QE times delta E over E plus 1/2 delta Z AA. And the electron field renormalization constant has cancelled, so this is what we get from here. And then from the second line we get plus E over 2 SW CW times delta Z ZA divided by 2 times gamma mu CRL times the unit matrix, and that is equivalent to saying the following: E times QE times delta E over E plus 1/2 delta Z AA minus SW divided by CW times delta Z ZA divided by 2. So, and then you have here a very nice result for the charge renormalization constant delta E over E which again, like in QED, depends only on gauge boson self-energies, and therefore we get charge universality just like in QED. I will repeat the last equation here at the beginning of the next lecture and then do the interpretation also in the next lecture, but you see it already here how it has emerged. From this complicated Watt identity, we then get basically the same conclusion as in QED, just with some additional modifications which make it look more complicated, but the physics interpretation is the same. Okay, so let us stop here and then continue next time on Thursday.